Welcome to the Math Record. Today we'll be introducing the concept of sampling distributions. This video will cover Chapter 1, Part 5 of our statistics class. Okay, what is a sampling distribution? So sampling distribution. Well, a sampling distribution is basically a way to calculate the probability of an event and determine if it's unusual. Going back to our previous video for Chapter 1 part 4, we introduced the concept of like means and standard deviations, and we're talking about like how unusual it'd be to, let's say, like if you like flip a coin 4 times, right? So you flip a coin 4 times and you get like heads, 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 when you expect it to have 2 heads and 2 tails because it's equal probability, right? So it's not in this order, but basically it's just equal heads and equal tails. So how unusual would that be? And we're gonna have there's basically a this is what we're gonna be using, a sampling distribution to find out. And these are basically just graphs, and we're gonna use numbers from standard deviations and means to find out. This is a really basic case, but you could just basically do this with easy probability. But there are ways to like there are like really weird that you can't just use standard probability to solve, and you have to use sampling distributions. Okay, there are actually multiple types of sampling distributions. There is the Z model. This is basically just a normal model. So it kind of looks like this. It looks kind of like a bell curve, but symmetric with both sides. So this side is equal to this side. It's symmetric, even though it kind of doesn't look like it because of bad drawing. But basically, where it's gonna be centered is called the mean, and where you're gonna draw it is and then you're gonna have like standard deviations right here. So let's just draw this again. Sorry about that. Okay, that's right. So you have mean right here, and then right here is the first standard deviation. This is the second standard deviation, and right here would be like the third standard deviation, and this one would be a negative standard, the negative a standard deviation away from the mean, and this would be two standard deviations from the mean. This would be 3 standard deviations from the mean, right? And that's basically the general gist of how it looks. And then it doesn't have to fall exactly 1, 2, 3 standard deviations. Like it could be 1.5, like right here. So then when we're probably calculating, when we're using this to calculate probability, what we do is that we're gonna see how many standard deviation it is away from the mean, right? So let's say it's right here, and then you're gonna see like if it's like, and then we're gonna calculate this probability, and this probability will give us a number out of this entire probability, out of this entire like area under this graph, right? So we're gonna say based on this probability that is it like unlikely to occur or is it likely to occur? Because like if you just look at it, it's really small, so it kind of like seems unlikely. Or you have something like right here, and you say it's above, so it has all this probability, and we say it's like really likely for it to occur. So it's not really that unusual, and that's what we'll be using, a Z model. So Z models are basically used to calculate proportions. It's basically just that simple. If you see any proportions and you want to use and you're using a Z model, if you're seeing a proportion and you're using a sampling distribution, you're gonna use a Z model. And there are different types of Z models. If you get like one proportion, then basically it's gonna be a one proportion Z model, or if you're using 2 of them, it's gonna be a 2 proportion Z model. And we'll be covering this more in depth in our in chapter 2, where we'll be covering both the 1 proportion and the 2 proportion, and we're gonna be explaining how like they differ and how to do like the math. Um, Other than Z models, the next thing that you'll learn would be the T model. This would be covered in chapter 3, and there's 3 types of them. There is a one sample. Sorry. There's a one sample. There's a 2 sample, and there's a paired. Okay. So basically, T models work with while Z models work with proportions. T models work with means or basically averages. So if you ever see a number just basically by itself, then you're gonna be using a T model. So a T model looks basically just like a normal model. So while a normal model looks like this, right? A T model is like more flattened. It looks something like this, right? So while this has like a really steep kind of like curve up, this one is less steep because because P models are focusing on means, so they're kind of a little bit more spread out. So a good thing to know is that Z models, their standard deviations are less spread out than T models. So while like let's say your mean is like right here, I mean, your mean is right here and your standard deviation is right here. If you have a mean right here, generally the standard deviation will be even further. It will be like right here. So it has a wider spread. You know how like IQR range and like standard deviation is calculated as spread? Yeah, so T models will have a wider spread. So it'll be able to cover more data because it's basically working with means, not proportions. So, and the last thing we'll be learning, which we're gonna be covering in chapter 4, will be chi-square models. There are, sorry, I forgot the E. Chi-square models. That's a Q. That's an A. There are 3 types. There's chi-square goodness of fit, which I usually refer as GOF because it's just easier to write it that way instead of writing this entire thing. Which chi-square goodness of fit, and then there's a chi-square test of homogeneity, and there's a chi-square test of independence. So goodness of fit, it's basically you're gonna use goodness of fit when you're working with basically one chart. So if you only have a frequency table, not a contingency table, it has to be a frequency table. If it's a frequency table, then basically you're just gonna be working with goodness of fit. So basically you have like let's say the let's say color and amount, right? So you have like red, blue, and then you have like 1 and 2. But and like some kind of company claims that their red is like 50% and their blue is 50% of their production, so they equal amount of reds and blues. Where you're gonna use a chi-square goodness of fit to see if the distribution of 1 to 2 is really that unusual. This is a really small case and is also a really bad case, but we'll be explaining this further in chapter 4. So if you see a frequency table, you're gonna use goodness of fit. If you ever see a contingency table, so basically you have like this, right? You have 1, 2, 3, and 4, right? And this is 3, this is 7, this is 4, and this is 6, and this adds up to 10. And you just kind of have some kind of variable here, this kind of variable here or something. And then if you're ever the difference between a chi-square homogeneity and chi-square independence is that homogeneity comes from 2 samples. So let's say you took a sample from a boy population and from a girl population, and then you want to compare them. Well, you're gonna use chi-square homogeneity because you want to compare if they're like the same. Hence the name homogeneity, because homogeneity is like homologous if it's like the same or something. And then chi-square independence. Chi-square independence is only one sample. So you're taking one sample and you see if one variable is like the same as another. Because while both of homogeneity and independence does seem like they have 2 variables right here and right here. So let's say it was like saying they go to college and like they which like kind of course they go to. So it's like yes or no, and then like take math or reading. Then basically you want to like for homogeneity, you take a sample where they go to college and take a sample where another sample where they're not in college, and then you basically compare them. For test of independence, you just gotta have one entire sample, and you're gonna ask them if they are taking college or they aren't taking college, and then you gotta test and then you're gonna ask them which is their subject, reading or math. So you're taking one sample for independence, two samples for homogeneity. This is sometimes really easy to like tell based on like what kind of question you're asking. If you ever want to compare like groups, then basically you're just gonna have like homogeneity. But if you ever want to like talk about the actual independence, like it's pretty explicit if they want to talk about independence, then use test of independence. Um, Usually it's basically just the name that's different. The math is pretty similar for both of them, and usually just give the same answer. Goodness of fit is the one that's is the easiest one to know though. If you ever see a frequency table to remind you, basically it's just always use a goodness of fit. It has to be a frequency table. It cannot be a contingency. If it's contingency, it has to be one of the tests of homogeneity or independence. So, oh yeah, I forgot for something for like T models. For T models, the one sample is if you have one mean. Two sample is if you have two means. So one sample you want to just compare to like some kind of claim by the company. So let's say they claim that's 50%, but your sample has 30% average mean, or mean average. And then for T model for two samples, you have one sample which has 50% and your another sample that's 30%, and you want to see if it's like actually equal. So instead of like talking about a claim, you're gonna have to be comparing samples. And then the last one is paired. The paired would be like if you get like data that could be like similar to each other. So basically it will be let's say let's say SAT, right? The SAT. So basically, you have one person that took the math and the reading section, and they score like a 700, and then in math and like 700 in reading, versus someone that scored like a 650 in like math, and then like a 790 in reading, right? And you want to be well, these data are paired, right? So you want to see if there's a difference between the math scores and reading scores. So then basically, what you do is that you compare the math since one student took the math and the reading, you could pair them because these data could be paired with each other. So this data would be paired with this one, this data would be paired with this one. So you could be like 700 minus 700 is 0, and 650 minus 790 is negative 140. You could have negatives in when you're calculating these, which we're going to explain further when we're taking a lot of these sampling distributions. You just have to find what else you have to compare them to. So paired data, if it seems like it could be paired, then you could do it together. Just because like you cannot confuse this with two samples, because if you're taking a sample, like say from a boy, and then take another sample from like a girl, like you can't put those samples together as a paired because they're not the same people. But if you're taking like something like the SAT, one person took the math and the reading. Well, that one person took that math and that reading, so you could pair them. So basically, okay. So basically, in general, if you see any proportions, you're just gonna use a Z-model. So if you see one proportion, you're gonna use a one-port Z-model. Two proportions, you're gonna use a two-port Z-model. If it's not written as a proportion, you're just gonna use a T-model basically. So you're gonna use if you see one sample, you're just gonna use a one sample. If you see two samples, you're gonna use a two sample. And if you see like basically one sample, but they have like multiple datas from it, like the SAT, basically you're gonna use a paired. And then there is chi-square test. Chi-square test, if you ever see any charts, it's basically just a chi-square test. So if you see like a frequency table, which is it's gonna be a chi-square test of goodness of fit, a contingency table, you just gotta determine what question is asking for it to be a homogeneity or independence. So proportions, Z model. Means, T models. Chi-square test, charts. Which chi-square test is just to like show distribution, because while T model and normal models look like some kind of curve, right? So that's a Z model. This would be a so it's more flattened out is a T model. A goodness any chi-square model looks skewed, basically like this. So it's always gonna be skewed to the right, right? So because the tail is to the right all the time. So technically, the Z model would be just like a normal one that you always use with proportions. T models are more flattened out and has a wider spread. And chi-square test, chi-squared. It is basically skewed. And chi-squares are used for like distributions, and that's why they're using tables, because tables show distribution. So you see like a distribution like red, blue, and green marbles or something. Then basically they're going to use a chart, and then you're going to look at that chart, and you're going to be using a chi-square model. So for like neural models, there's a metric, as I said before, mean right here, standard deviation, and then you're gonna be start using something called for Z models, you're gonna be use something called Z score. Oh, sorry, it's something called Z score, which is Z score is basically just whatever the value you get, which you're gonna use based on your sample. We're gonna explain further in future videos. To subtract it by the mean and then divided by the standard deviation. So ZModel doesn't really fit anywhere into like our in your graph. You could basically just make a line that I did like right here and call it the Z score. But basically we're gonna use this Z model for our calculations, mostly when you're plugging into your calculator. Whenever you're doing sample distributions, you're most likely just gonna use your calculator. This is really hard to do it by hand unless you're using some calculus technique. And then when you're working with T models, right? T models, you're gonna be working with T score. So Z score for Z models, T score for T models. T model is basically the same idea. It's basically just whatever that value is minus the mean, which is gonna be like divided by the standard deviation. Because while the mean for the Z score is gonna Z is a proportion, and then you divide by a proportion for the standard deviation. Basically, standard deviation doesn't really like count for anything. It's just the mean is gonna be a proportion, while the mean for T score is gonna be a mean and average. So you're just gonna divide by standard deviation, and you get like a T score. So the T score would be like the Z score of the T model, basically. And then for chi-square test, chi-square doesn't have anything. Chi-square doesn't have any scores because since it's not symmetric, you can't really do any like tests. Kind of like you could do tests with it, but you can't like do any of these z scores to do. You're gonna be working with something called x squared. The x squared will be what you're gonna be called. I don't know what the exact name is, but basically you're gonna be looking for x squared, and you're gonna be comparing like the distribution. And basically, what we're gonna be this is very important. Like once you're gonna be calculating like area under a curve, so the area under the curve would tell us the probability is equal to the probability. So what's the probability that's gonna be like greater than like one standard deviation? So if it's greater than one standard deviation, then this is our area, and then the area is our probability. So as we say, it's not really that unlikely because it seems likely because like there's such a lot of area, so a lot of the data could be accounted for. So basically, you're gonna be learning two of them. You have to find the area under a curve using basically your calculator. So you're not gonna do any of the really hard math. You basically just plug in the values, and you'll get the area. And there's also the inverse area, which they give you the area, and you wanna find the basically the statistics. So like the z score, the t score, and the x squared basically. So that's why you want to use the inverse area. Both of these would be very important. I'll be using this in our future chapter 2, chapter 3, and chapter 4 for our chi-squared, for our t models, and for our z models. But basically, I'm gonna be using a Nspire. If you're using a TI-84, um, I'm sorry, I really don't know how to work with those. So, and also there's two things you might want to know. There is the central limit theorem. So we're going like things you need, like concepts you know right now for sampling distributions. There's the central limit theorem, which is kind of intuitive, like a bunch of math theorems are. Which is like if you add more sample size, so if n is getting bigger, right? And a sample size. So then you have a better sampling distribution. So basically, what it has is, let's say you have a sample of a hundred versus a sample of like 1,000. 1,000 would be more precise because there's more people, right? So then less of the variation goes out. So that's what we use for central limit theorem, where you increase your n. It's just for you to know. It's not going to be something that you're going to use for calculations and stuff. But they would be used if you're taking the AP exam. Usually, they sometimes ask something about this, where they ask like central limit theorem, where like if you add like a bunch of n's, it's gonna start increasing. There also is like a bunch of other laws, but they're also really self-intuitive if you ever search them up. Which like I'm not sure if this is the exact term, but it's like law of averages, which basically if you add a lot of n and like let's say you get like a coin, right? Yeah, you flip a coin and you flip it like 1,000 times. Like averagely, it should have equal amount of heads and tails. So as you do this like infinite amount of times, then basically it's gonna be equal. So that's what it means for like law of averages or something, or a law of large numbers. I'm not exactly sure. For this one, when you're calculating for standard deviations and you're really lazy, and it's basically really close to like one standard deviation away, or like two standard deviations away, or three standard deviations away, then basically you can use this rule called the 68, 95, 99.7 rule. So if they're one standard deviation away, it's gonna be a 68%. If it's 95, if they're two standard deviations away, it's 95%, and if it's three standard deviations away, it's 99.7%. So basically, let's say you have a norm model like the Z model, right here, and then you have a mean, and let's say this is one standard deviation, this is two standard deviations, and these are like three standard deviation, right. So basically, they're saying that one standard deviation, this entire area over here, is equal to 68% of the entire area under this curve, right? And if you add these areas for two standard deviation, you're gonna have 95%. And if you add these areas right here, you have a 99.7%, basically. And that's what the rule is. Like, it's something that you don't really need to prove. It's basically just used with a calculator, and they just found the values, and they just made this into a rule. So if you just have it's good. It's good to know if you don't want to do any calculations. That basically covers the sampling distributions. Now let's move on to like confidence intervals. So delete this. Now we're gonna be working with confidence intervals. Okay. So basically, after you're using like sampling to distribution to determine an event unusual, we use confidence interval to give us a general idea like where the actual proportion or mean really is. Because the sampling distributions don't give us like an actual answer. It tells us if the thing is unusual or not. So it's like a yes or no question, and then we follow it up with a confidence interval. And the ones I told you as before, you can only use a confidence interval for a Z model and for a T model because they are symmetric. So you can only use confidence intervals for symmetric models. You can't use it for skewed, like chi-squared. So for Z models and for T models, you're gonna follow it for like a confidence interval. So let's say you have a mean of like 0.5, right? And you have like a margin of error of like 0.2. Then your confidence interval is like 0.3 to basically 0.7 because 0.5 minus 0.2 is 0.3 and 0.5 plus 0.2 is 0.7. So you have like a confidence interval. And there's always like some kind of confidence. Like let's say like you are 95% confident that the margin of error is like 5.2. So you have a 95% confidence interval of 0.3 to 0.7. So we'll be explaining this further in our future videos. But basically, this is the general idea. You're gonna use confidence intervals so you could tell us where the general gist of like where the like usualness kind of falls in, but it doesn't really tell us the exact amount. So if you ever see something like in the news or stuff, like statisticians always say like they're like 95% confident that it's between these areas. What they're doing is that they're looking for an area under the curve, and then they're basically finding out where that kind of ranges out, so they could get as most data as possible. So It doesn't mean that like something that's like, let's say you have an interval between like 0.3 and zero point 0.5. It doesn't mean like something 0.7 is not gonna be able to happen. It's just unusual, but it could happen, even though it has such a really low probability. So usually, when you're using for like the area and inverse area, for area you're gonna be using for sampling distributions because you're looking for the probability. So the area gives you the probability, and inverse area will give you the confidence interval because you want to get 95% of the area, so a 95% confidence. So you inverse 95, and then you get that number, and that number helps you find the margin of error, and that gives you the entire number to do. And that's why it's important to use for z scores and t scores because it's usually calculated by mean plus or minus like whatever a z or t times the standard deviation, and that's basically how you're going to find like confidence intervals. So, but that doesn't always have to be done. But following up with a confidence interval basically gives us a general idea of like where the data is centered, because a test would be pretty useful and a to like determine if it's like unusual or not. But confidence interval could also be used for the same way, but it also gives you like some math of where it is. But you don't always have to do it. If the question doesn't ask for it, you don't have to do it. So if they ever ask for a test, just do a sampling distribution. If they want you to follow it up with a confidence interval, then you do a confidence interval. But if you want to prove it more with the confidence interval, you could. You don't have to because the test will already give you enough evidence. Because you're never 100% likely, but you have to put everything in context. So you're gonna always have to be like, you're not 100% likely that this event occurs, but you're gonna you could say that it might be probable. So that's what it is. You're never 100%, but you are either likely, you're not likely, or like you're basically kind of unsure sometimes. But we'll basically go more in depth about this in like future videos, where we're gonna be talking about each of these models and we're gonna give some examples for you to understand. You just need to practice more of these models and you get a basic idea how they work. Well, thanks for watching, and I'll see you at the next math record.